All right. Welcome, everybody, to the Georgia Tech Graph Theory Seminar. Our speaker today is David Wood from Monash University in Melbourne, Australia. It's 7:45 in the morning there right now, and he will tell us about universal graph product structures.
Thank you, Anton, for the opportunity to speak in your seminar this morning. I wanted to talk about a real research direction in this seminar, not just about a single paper. I'll be surveying about 3 papers, hence the long list of co-authors here. There's been very exciting developments in the last couple of years, and this photo was taken in very happier times, 2019. This was taken about half an hour after we made the first breakthrough on this in this area. We're all very excited about this, about it, and it's really developed since then into a new theory and a sort of new approach for studying problems about planar graphs and other more general graph classes. So first of all, let me set the scene with a little bit of background on sort of graph structure theory. Here's a picture of what graph structure theory looks like. So in this picture, these graph classes are shown, and the black arrows indicate containment. So at the bottom of the picture, we have forests, which are probably the simplest minor closed class. Then they are a subset of planar graphs, and planar graphs are graphs that can be drawn in the plane without crossings. These are special cases of graphs of bounded genus. So pick your favorite surface, a torus or a projective plane, and you take the class of graphs that could be drawn on that surface with no crossings. That's what we get here. Then these are subsets of minor closed classes. All these are examples of minor closed classes. So what does this word minor mean? A graph, think of it as a small graph is a minor of a big graph if the small graph can be obtained from the big graph by vertex or edge deletions and edge contractions. So edge contractions are the important thing here. To contract that red edge means you delete the red edge and you squish the endpoints together and always replace parallel edges by a single edge. So all these are examples of minor closed classes. If you take a planar graph drawn on the plane with no crossings and you do an edge contraction, well, you maintain planarity. So this is an example of a minor closed class. So there's a large body of literature on minor closed classes, most importantly, the seminal work of Robertson and Seymour. And one of the main theorems, or probably the main theorem of the work of Robertson and Seymour, is what's called the graph minor structure theorem. And this is an incredibly powerful theorem. And what it does is that it describes all the minor closed classes in terms of simpler classes. So I'm not going to state it formally, but what Robertson and Seymour do is they have some sort of basic building blocks and then a set of basic operations. And then they show that graphs up here, up in the top, can be any graph in any minor closed class can be described in terms of these basic building blocks and these basic operations. Now, one of the basic building blocks in the Robertson and Seymour graph minor structure theorem is planar graphs. So planar graphs sort of sit at the bottom of the picture. They are one of the building blocks, and in fact, they are the simplest building block in some sense. So this suggests this question, and it's a question that's bothered me for many years. And the question is basically, well, what is the structure of planar graphs? Can you describe planar graphs in terms of something simpler? And Robertson and Seymour don't answer that question. And the punchline of this talk is that you can describe planar graphs in terms of something simpler. And the something simpler turns out to be graphs of bounded tree width. I'll define this in a minute, but just for now, think of tree width as a measure of how similar a graph is to a tree. And graphs of bounded tree width are tree-like graphs. That's all you need to really know for this talk. They're just tree-like graphs. They're also a minor closed class, so they fit into the original picture. Now, I claim that we really are describing planar graphs by something simpler. Graphs of bounded treewidth really are simpler classes than planar graphs. And this is exemplified by the dichotomy in between easy and hard problems. So for example, most NP-complete problems sort of stay NP-complete on planar graphs. So planar graphs typically are hard instances of computational problems, but most problems become easy on graphs of bounded treewidth. For example, Courcell's theorem says that any problem that can be described in monadic second order logic can be solved in linear time on graphs of bounded treewidth. So these are typically easy problems. So I think it's fair to say that describing planar graphs in terms of bounded treewidth graphs is a simpler class. And so these red arrows are what I'll be talking about today. And well, what we're going to do is we're going to describe planar graphs via what's called a product structure theorem. And we'll describe them in terms of graphs of bounded treewidth. So the nice thing about this product structure theory is that, I should say that graphs of bounded treewidth, it should be no surprise that they appear in this picture, because indeed graphs of bounded treewidth appear in the graph minor structure theorem of Robertson and Seymour. Indeed, they invented the definition of treewidth. Now, the nice thing about this product structure is that it actually says something new, not just about planar graphs, but also about graphs of bounded genus, or indeed any minor closed class. So we've got something new to say about all these things. And finally, the new direction that we're taking this is that these product structure theorems are useful for describing even non-minor closed graph classes. This work sort of sits beyond minor closed classes, and it starts being relevant for the Nessa-Trilosona de Mendes graph sparsity theory, if you're familiar with that. Finally, we get what I call universal graphs for these classes. So that's the other thing that I'll be talking about in today's talk. So try and remember this picture for the remainder of the seminar, and this is basically a table of contents for what I'm going to be talking about. I'm going to be talking about the red lines and the green blob. Okay, so let's start off with what's treewidth. Well, here's the definition, but you don't really need to understand this definition for the sake of the seminar. But a tree decomposition represents each vertex of a graph as a subtree of a tree, so that subtrees of adjacent vertices intersect in the tree. So here's your graph up here, and down here is a tree decomposition of the graph. So each vertex is represented by a subtree. So vertex B is represented by this path through there. And the property is that if two vertices are adjacent, then they appear in a common bag. So B and E are adjacent, and there they are sitting in this little bag, which we call here. So this turns out to be a very good definition. And we define the width of the tree decomposition to be the maximum size of a bag minus 1. So here this decomposition has width 2. And we define the tree width of the graph as the minimum width of a tree decomposition of the graph. So for example, if all the bags have size 2, then you can show that the graph is actually a forest. And in fact, graphs have tree width 1 if and only if they're a forest. And this is tree width turns out to be a very good, robust measure of what it means to be like a tree. It's also a minor closed class, graphs of tree width at most k for any integer k. Okay, that's the definition. You don't really need to know that for the talk. It's just think bounded tree width means simple like a tree. So what graphs do not have bounded tree width? And the canonical example is the n by n grid. This planar graph here, it has tree width n. You can see for yourself that this does not look like a tree, hopefully. And it is the canonical example because Robertson and Seymour proved that every graph with large tree width contains a large grid minor. Having a grid minor is like the certificate that says the graph has large tree width. Now, there's an easy exercise that says that every planar graph is a minor of some grid graph. So on the left here, I've got the octahedron. And on the right, if I contract the red blobs and delete the outer face, I would get back the octahedron. And it's easy to show that every planar graph is sort of sitting in here in this grid as a minor. So you put all these notes together and you get the following important theorem of Robertson and Seymour. And it says a minor closed class G has bounded tree width if and only if some planar graph is not in the class. So this exemplifies in a structural sense that planar graphs are like the first hard minor closed class. Like the simple ones are the bounded tree width, and as soon as you move up to planar graphs, it becomes hard. But planar graphs really are the first class that you see that are hard, because as soon as you take any minor closed class that doesn't have some planar graph in it, then it must have bounded tree width. So planar graphs are really the point where classes become hard, and this is why graph theoretically planar graphs are important. It's not just a curiosity, some topological curiosity, related to the four-color theorem. They really are a key class in this broad picture of minor closed classes. Okay, so now let's jump to the main theorem of the talk. And this is our product structure theorem for planar graphs. So it says that every planar graph G is a subgraph of H times P, where H is some graph with tree width at most 8 and P is a path. So take a moment to digest this. Now, probably the key word here is where's my cursor gone? Oh, my mouse has disappeared. Anyway, the key word is subgraph. Here's the key word, subgraph. Like, for example, on the previous slide, I said every planar graph is a minor of a path or a grid, which is sort of like a path times a path. But now we've got subgraph. This is a much stronger relation. Now, the class that G is a subgraph of is these H times P's, where H is a bounded tree width graph. And the product that we're looking at here is the strong product. This is this box with a cross in it. So let's see what this strong product means. Down the bottom, I've got a graph H here, which certainly has bounded tree width. It's tree width 2. And here on the left, I've got a path. And so the product is shown in the green, and each row is just a copy of H. Each column is a copy of the path. And for every edge of H, you look at, and every edge of the path, you look at the corresponding 4 vertices in the product and you add the cross edge. Right? That's what you mean by H times P. This notation sort of describes the definition. So throughout the talk, I'll be talking about these strong products. So it's not obvious, but it turns out the theorem says that every planar graph is sitting inside one of these H times P's, where H is bounded tree width. The number 8 really isn't that important. The important thing is that it's a constant in the tree width. So this is the theorem that I'll be discussing at some length. Let me give you a hint about the proof. I'm not really going to be talking about proofs in this seminar very much. I'll just give you a hint. Anyway, the starting point for this theorem is a beautiful theorem of Philipp-Truk and Siebitz, which just predates ours by a year or so. And they proved that every planar graph has a partition of its vertex set, script P, into geodesic paths. What does that mean? Well, a path in a graph is a geodesic if it's the shortest path between its endpoints. So you can partition the whole graph into geodesic paths, and then this notation G/P means contract each of the paths in your partition down to a single vertex. So you think of it as taking a quotient from this partition, and then the graph after doing the contraction has bounded tree width. It's a lovely theorem, and it has an absolutely beautiful proof, highly non-obvious, very clever induction setup. So what we did is just took their lemma and tweaked it a little bit. And this is how we tweaked it. We said, take any BFS spanning tree of a planar graph, then you have the same setup. There is a vertex partition, but now we say that the paths of this partition can be found in the tree. And they also have the property that they're vertical within the tree. So vertical means, well, this tree's rooted. A vertical path means it starts at some vertex and goes towards the root. hopefully the word vertical describes that. And then we get the same conclusion, that is, if you contract all the paths, you get a graph of bounded tree width. So this picture hopefully tells the story. The red tree on the left is a BFS spanning tree of the graph. And then the blue paths are the partition. So BEJ is one of the paths in the partition. And they're all, each of the blue paths is vertical. Right? ADIO down the right-hand side is a long vertical path. And now if you contract all the blue paths into a single vertex, yes, you will get a graph of bounded tree width, of course, but this is true now for every planar graph. Now, what has this picture got to do with products? Well, we take this picture that we just had and now just redraw this picture, but draw each of the vertical paths in the tree vertically. Think of it geometrically. You just redraw the graph, and each of these blue paths is now a vertical line, and hopefully you see that this is looking like a product. Because if you contract each of the blue paths down to this brown graph, now this picture is just a subgraph of the brown graph times a path, because every edge has to go between two layers or within a layer because it's a BFS spanning tree. And take any edge such as KF, well, KF has to project down to this edge in the brown graph. And that's basically the definition of a strong product. So this says then that the original graph G is a subgraph of the brown graph times a path, but this brown graph G contract P has tree width at most 8. So this is the main ideas of the proof of the product structure theorem for planar graphs. And basically, to prove this previous lemma, this one up the top, all we do is take the Philipchuk-Siebert's proof and add the spanning tree and show that with their proof, you can just find all the paths in the spanning tree. The last comment is that you actually don't need BFS here. The lemma is still true, even if you don't take a BFS spanning tree. It works for any spanning tree, but we're going to apply it with a breadth first search spanning tree. Okay, so here's that main theorem again. I should say, please interrupt at any time if you've got questions. Every planar graph is a subgraph of H times P, where the tree width of H is at most 8. So hopefully you see the connection to the original picture. We're describing planar graphs in terms of something simpler. The something simpler are these tree width 8 graphs. Okay, so what? What is it good for? Well, it turns out this is good for lots of things. And I want to describe one application of this theorem. And the application is to a topic that I really like. It's called non-repetitive graph coloring. This is the topic that's at the intersection of the combinatorics of words and graph coloring. So first of all, what is a repetitively colored path? Well, we say a path is repetitively colored if the sequence of colors on the first half of the path exactly equals the sequence of colors on the second half of the path. This is an important topic in combinatorics of words. So then we say a coloring of a graph is non-repetitive if no subpath is repetitively colored. So we want to avoid repetitively colored paths. Now, if you take this 3 coloring of the 8 cycle on the right, you can check every path is non-repetitively colored. Like take this 4 vertex path here, blue, red, yellow, red. That's non-repetitive. But take a 1, 2, 3, 4, 5, 6. This is yellow, red, blue, yellow, red, yellow. That's non-repetitive. And you can check every path satisfies this property. So this is a non-repetitive coloring. And so we denote by pi of G to be the minimum number of colors in a non-repetitive coloring of a graph G. So the famous theorem in this area is well over 100 years old by Tui, and he proved that paths are non-repetitively 3-colorable. And that's actually completely non-trivial theorem, because you have to consider every subpath of this enormously long path. But the proof of Tui is absolutely gorgeous, because he showed that if you start with any non-repetitively colored path, this orange, blue, green, orange one, and you just take this replacement rule. You replace each orange vertex by this subpath, and then a similar rule for blues and greens, then you can prove, and it's not difficult, that the new coloring is non-repetitive. And so you just keep applying this replacement rule again and again, and you get an arbitrarily long, non-repetitively colored path. But it was in a paper of Alon Gwichik, Haluchak, and Riordan who said, well, let's not just do paths, let's do any graph. Tui didn't talk about paths, he talked about words. But you can think of it for any graph. And in this original paper of Alon et al., they proved using a beautiful application of the local lemma that graphs of even any max degree have got bounded non-repetitive chromatic number. And in fact, the bound is only delta squared. Now, in this original paper of Alon et al., the main open problem that they left was, do planar graphs have bounded pi? And this was recognized as the most important problem in the field for close to 20 years. And the short answer is, the answer is yes. And product structure theory answers this question in a very easy way. So let's see it. Well, the first ingredient you have to think about is bounded treewidth graphs. And well, thankfully, Kundgren and Palsmeyer had already answered the question for bounded treewidth graphs. Bounded treewidth graphs do have bounded non-repetitive chromatic number. Now, what we did is we needed to introduce a slight strong variation of the non-repetitive chromatic number. I'm not going to go into that technical detail right now, but it's just one extra property. And we call that pi star of G, the strong non-repetitive chromatic number. Now, the reason we need this strong version is because we want to prove a lemma, this one here, for products. And so we prove this lemma that says pi star of H times P, where P is a path and H is any graph, is at most 4 times pi star of H. So you need the strong property to get this lemma, because you want strong on both sides. Then this is an easy lemma once you see the right definition of strong. Then the lemma of Kundgren and Palsmeyer generalizes for strong with an identical proof. And so now you just put it all together. So it's like building blocks. You take any planar graph G. Pi of G is at most pi star of G. By the first lemma for products, by the product structure theorem, what I mentioned earlier, and G is a subgraph of H times P, where H has got bounded treewidth. Obviously, non-repetitive chromatic number is closed under taking subgraphs. And now by the first lemma up there, pi star of H times P is at most 4 times pi star of H. But H has got bounded treewidth. So by this lemma, we get that the pi star of H is at most 4 to the power 8. So we finally get this bound 262,000 on the non-repetitive chromatic number of planar graphs. So this answers the question of Alon et al. And really the key ingredient is the product structure theorem. And once you've got that, the rest is just a couple of fairly straightforward lemmas. So hopefully you see the power of this product structure theorem, because it reduces problems down to, all you need is 2 ingredients to solve them. You need a lemma for bounded treewidth graphs, and then you need a lemma for products. And you put the 2 together and you get a result for planar graphs. Now you're probably thinking 262,000 is a lot of colors, and you'd be right, but thankfully we can reduce the number of colors. And the lemma is to reduce the number of colors is of independent interest, because we prove another product structure theorem for planar graphs where we've added this K3 on the right here. We say every planar graph is a subgraph of a product of H times a path times a triangle. And the gain is that the treewidth has dropped a lot down to treewidth 3. And treewidth 3 is best possible here. You can't improve the treewidth 3 bound even if you allowed the other 3 to be 1,000. So treewidth 3 is best possible. But if you plug in the previous mechanism with this new theorem, you reduce the number of colors down to 768. Okay, now there's a lot of other applications for this product structure theorem. There's been a huge amount of activity in the last 2 years, say. Let me just mention a couple of the applications very briefly. Q number was the the starting point of this work. I'm not going to define what this parameter is. It's just a parameter that people care about. Let's just say that. But it's the same paradigm for solving, for proving that planar graphs have bounded Q number. First of all, you show that bounded tree width graphs have bounded Q number. That was done some years ago. But then you have a lemma for the products. The Q number of H times a path is at most 3 times the Q number of H plus 1. And you just put the two things together and you get a bound on the Q number of planar graph. And that was the main open problem in that field, where the planar graphs have bounded Q number. And that was the original motivation for developing the product structure theorem. One more application is in this area of graph encodings. Now, if you're a computer scientist, you'll talk about adjacency labelings, which is like an efficient way to encode a graph. The more graph theoretic way to think about it is as a universal graphs under the induced subgraph relation. So imagine you want to define a graph U that contains every planar graph on n vertices as an induced subgraph. And now it turns out that you can get a very small graph U with that property. And this is the beautiful theorem that was proved by my colleagues. I'm not an author on this paper. They showed that for every fixed integer k and integer n, there is a graph U, and it's got just a little bit more than n vertices, n to the power 1 plus little o of 1. And it's universal for any graph which is a subgraph of a product of a tree width k graph and a path, and it's got n vertices. So U contains every graph G as an induced subgraph, where G is a subgraph of H times P, where H is tree width at most K and G's got n vertices. It's a lovely theorem. And now you just apply the previous results with K equal to 8, and you get a result for planar graphs. And this improves a long sequence of theorems where this exponent here, well, it started off at about 6, then came down to 5, and then to 2, and then to 4/3, and finally to 1, which is of course optimal here. So the product structure theory is again the key ingredient, although you need to do quite a bit more work to construct this graph U. This is an absolutely beautiful paper. If you have any interest in data structures and graph theory, then I highly recommend reading it. It's a real masterpiece of data structures and graph theory combined. And there are other applications to things like p-centered colorings, clustered graph coloring that I won't go into. And there's even other applications that aren't mentioned on the slide. There's been a lot of activity in this area lately. Okay, there's the main theorem again, just to rub it in. Every planar graph G is a subgraph of product of H times P, where H is tree width at most 8 and P is a path. Okay, now a good question to ask is H universal here? Does H depend on G, or can you define H to be to something as a fixed graph? And the short answer is yes. You can take H to be universal, but the long answer is more interesting. And for the long answer, you need to really look at infinite graphs. So let's take a little bit of a sidestep and talk about infinite graphs for a while. And this topic goes back to a question from Ulam from, I think, the 60s even. It's not in any paper, but other papers say that Ulam asked this question. And he asked, is there a universal countable planar graph? What does that mean? All right, so we're in the world of infinite graphs. He's asking, so you take the class of all countable planar graphs. These are graphs that can be drawn in the plane with no crossings, and the number of vertices is countable, meaning the number of vertices is the same as the size of the set of integers. Now, does that class contain a universal graph, meaning there is some graph U that is countable and planar, and it contains all of the countable planar graphs as subgraphs? That's a really good question, and that it's not at all obvious what the answer is. That's why I asked the question, of course. But the answer was given by Pach in 1981. This is one of Janosch's very first papers. It might be his second paper, I think. I think this is roughly what Janos Pach looked like in 1981. He's a little bit older now. So Janos answered Ulam's question. He said no. He said there is no universal countable planar graph. And the proof is really lovely. I'm amazed that this paper of Janos has barely been cited. It's a beautiful proof, and not many people seem to have noticed this paper in the literature. It really is lovely. So, and it gives a short, quick argument about why there is no universal countable planar graph. Okay, so with my first of all, we can rewrite Pach's theorem in a long way, and here's a very long-winded statement of it. It says if U is a countable graph and it contains every countable planar graph as a subgraph, then U must contain K5 or K33 as a minor. This is the same as saying U is not planar. Now, it turns out that we can prove a much stronger theorem. There's nothing special about K5 or K33 here. So with co-authors, we've shown that if U is a countable graph that contains every countable planar graph as a subgraph, then in fact, not only is there a K5 or K33 as a minor, there is in fact an infinite complete graph minor, K A left not. So it's very strongly non-planar, this graph U. It has an infinite complete graph as a minor. So this is the bad news for universal graphs for planar graphs. There is no such thing, not even close to one. There is every graph that contains all the planar graphs has to contain an infinite complete graph as a minor. So that's the really bad news. Let me say a couple of things about this proof. Let's define a frame F to be this infinite grid plus the edges on the main diagonals. Call that a frame. And now you'll notice that there are uncountably many triangulations of the frame because there are countably infinite faces of size 4. And for each face of size 4, each of those squares, you've got two choices about how to triangulate the face, 45 degrees or negative 45 degrees. So that means you've got a choice at every face. Well, that means there's uncountably many triangulations of this frame graph. So what we then prove is the following lemma, and it says if G is any uncountable family of triangulations of the frame, and U is a countable graph containing every graph in G, then this U must contain some triangulation in your class plus infinitely many disjoint jumps of T. So what is these disjoint jumps? So this is what's shown in green here. So a jump of T in U is a path in T where the endpoints, say A, B, are non-adjacent vertices in T, and then there is a path where the internal vertices of the path are outside of T. And all these paths are pairwise disjoint, and there are infinitely many of them. So that's what we showed. And you don't have to take all of the triangulations of F, just any uncountable family of triangulations. And then once you've found this triangulation T with the disjoint jumps, then you can show that any such setup, if you have U as any graph that contains a triangulation plus infinitely many disjoint jumps, then you do have an infinite complete graph as a minor. So these are the two lemmas that imply the theorem above. I just want to give you a sort of a hint about how we proved this. I should say that this paper that's cited here is fully written, but it's not released yet. It turns out that we've now got 3 proofs of this theorem at the top. So we're currently working out sort of what to omit from the paper. As soon as we do that, we'll put it on the archive. Okay, so that's the bad news for universal graphs or planar graphs, is that you can't avoid an infinite complete graph minor in a universal graph for planar graphs. But the question remains. I mean, let's reword Ulam's question. Instead of saying, is there a countable planar graph? Well, let's say, well, what is the simplest graph that contains every countable planar graph? That question remains. And so it all depends how you measure simplicity. But there's lots of ways to measure simplicity, but we'll talk about that in a second. And what we showed is that you do get a graph that's pretty good as a universal countable planar graph. It's not planar itself, but it still has lots of the properties of planar graphs. And the particular graph that we define, and this is a single graph, is T7 times a path. Well, it contains every countable planar graph as a subgraph, where TK is a universal tree width K graph. So we can define that explicitly. And the definition is of independent interest, but I'm not going to go into that in this talk. And P is an infinite one-way path. Now you're probably thinking, wait there, what 7? That should be an 8. In the previous slides, in the finite case, we had tree width 8. Well, actually, one of the other things we did in this recent paper is show that the tree width 8 bound can be brought down to 7, but that's really not the punchline. The point is that we have a single graph, T7 times P, and it contains every countable planar graph as a subgraph. So the proof of this theorem uses the sort of classical tools of infinite combinatorics. We use Koenig's infinity lemma, and we use Zorn's lemma to reduce the question down to the planar case. But some of these using these tools are often straightforward. This proof wasn't completely straightforward, that the finite case implied the infinite case. You do need to do a bit of work to do that. So is this good? Is this a simple graph, T7 times P? That's a question you should ask yourself now. I mean, so what? You could take an infinite complete graph that contains every countable planar graph as a subgraph. Is this interesting? Well, I claim that T7 times P actually does have many of the core properties of planar graphs. It's definitely not planar, and it must have an infinite complete minor, but it still has many of the properties of planar graphs. Now, these are some of the properties. Some of you might know these definitions, some of you not. It has linear expansion of finite subgraphs. So this is linear expansion in the definition of Nesetril and Asona de Mendes. I'm not going to go into what that means, but I think this is one of the core properties of planar graphs. It has strong R coloring numbers, linear and R. Again, this is another core property of planar graphs. It implies all sorts of theorems about coloring planar graphs, such as bounded acyclic chromatic number and other things. This is a very generic measure of sparsity, really. Another one that is that every n vertex subgraph of T7 times P has big O of root n tree width. So this implies that every n vertex subgraph of T7 times P has got a root n size separator. So this theorem implies the Lipton-Tarjan separator theorem for planar graphs, which is, I think, a very good measure of whether this universal graph is a good universal graph for planar graphs. Planar graphs have root n size balanced separators, while every n vertex subgraph of this T7 times P has a balanced root n size separator. So that's a very important property that any universal graph should have, and it does. Okay, and in fact, we get another universal graph where we can drop the tree width down to 3. We get T3 times P times K3. And we can improve these two theorems a little bit by considering something called simple tree width. I mean, what is simple tree width? This is a notion that's in a handful of papers in the literature. So a tree decomposition, we say, is K simple. If each bag has size at most K plus 1, that's the normal definition of tree width. But with the extra property that each K set of vertices appears in at most 2 bags. Now this turns out to be, and then we say simple tree width of a graph is the minimum K such that G has a K simple tree decomposition. Now this actually is interesting. Let's, for example, in the small values of K, you get naturally defined classes. So remember, tree width 1 means the graph is a forest. But if you go to simple tree width 1, the class drops down to being a path. It's even simpler. Tree width 2 means the graph is what's called series parallel. But if you go to simple tree width 2, it's a smaller class, and that corresponds to outer planar graphs. And simple tree width 3 corresponds to the graphs of tree width 3 and the ones that are planar. So planarity appears in this notion of simple tree width. And what we actually show is that one, there is a universal simple tree width K graph. We call that SK. That's a fairly easy exercise, although you need to use Zorn's lemma in there. But then we get universal graphs for planar graphs using simple tree width. And this is probably the strongest theorem we have, is that S7 times a P contains every countable planar graph, and also S3 times P times a triangle contains every countable planar graph. But why do I like this theorem is that now is that S3 is planar. Right? Now our universal graph at least it starts with a planar graph. S3 is a planar graph. It's probably my favorite graph of all. Here's S3. You start with a triangle, and then you put a vertex in the middle of the internal face adjacent to the 3 vertices of the triangle, and repeat. Pick any internal face, put a vertex in the middle of it adjacent to the 3 vertices of that face, and you repeat that forever, and you get this graph S3. That's the universal graph for simple tree width 3, and that appears as the starting point of our universal graph for all planar graphs. So you take S3 that's shown here, times it by this path that sort of comes out of the screen, if you like, and then you take 3 copies of it, and you multiply that by the triangle, and you get a graph that contains every planar graph. Now there's a lovely open problem here, is whether you can you drop the triangle? Is S3 times a path, does that contain every countable planar graph? It's possible that that's true, but we don't know. That would be a lovely theorem if it was true. Okay, all right, I think that's all I want to say about planar graphs. Let's sort of talk about generalizations now. The first generalization is to graphs on any surface, and everything generalizes. Take any graph of Euler genus G. Euler genus is a notion that includes orientable and non-orientable genus, and you get these theorems here that says every genus G graph is a subgraph of something. Now this plus, the plus here just means the complete join. So you take a tree width 8 graph, complete join to a bounded size complete graph, and then times that by a path. And then there's another theorem here where it's just a single vertex times a path times a bounded complete graph. The proof of these theorems use a cutting lemma. So we take a graph of genus G, you can sort of cut through the surface, and when you delete the vertices in the cut, everything collapses down to the planar case. So then you apply the previous results for planar graphs and then stick back the vertices of the cut, and you end up with this result. And for example, all of the previous applications work in this setting. So for example, we get the following linear bound on the non-repetitive chromatic number as a function of the genus. And you get universal graphs for these classes. Everything just goes through. Now, what about general minor closed classes? It gets a bit more complicated, but still we are able to prove this description of any minor closed class. Let's read it. It's a little bit complicated, but this is what it says. It says, take any minor closed class. So these are going back to the picture at the start of the talk, this is the class right at the top. There are fixed integers K and L, and every graph in the class has a tree decomposition in which each torso is a subgraph of this thing here. There, H times P times plus KL, where tree width H is bounded times a path plus complete join with a small complete graph. Now this word torso means you have a tree decomposition. Now if 2 bags intersect, you add a clique on the intersection, and then the torso is what you get from a single bag plus a clique on the intersections of neighboring bags. So this is proved using the graph minor structure theorem, but it's very useful, this description, because it simplifies a lot of the things in the graph minor structure theorem. There's no mention of surfaces, there's no topology, there's nothing called vortices, which are a tricky thing to deal with in the graph minor structure theorem. And this is a very useful and applicable version of the Robertson-Seymour graph minor structure theorem in terms of products. So it implies that, for example, non-repetitive chromatic number is bounded in minor closed classes, and even you can get in any topologically minor closed class. So that includes excluded subdivisions. Remember, it was open whether you could do, whether planar graphs have bounded non-repetitive chromatic number. We can actually do it in any minor closed class and even more. There's another simple consequences of this theorem, which is something called low tree width colourings. So there's a beautiful theorem of DeVos et al. Says, take any graph in a minor closed class, then you can partition the vertex set into two parts, and they both have got bounded tree width. And this is really a very simple consequence of this theorem above. The previous proof had some sort of hardcore graph structure theory in there. It's once you know the theorem above, it really is just a straightforward corollary. And we get universal graphs. So this is a universal graph for really any minor closed class. And here's the statement. For every fixed graph X, there exists a universal graph U. Now, U is explicitly defined in our paper, but I'm not going to define it here. The definition just gets technical, but it is an explicitly defined graph. And U is very well behaved. It has what we want. It contains all the X minor free graphs. X is the excluded minor here. But it has all the other good properties that we said for planar graphs. Linear expansion of finite subgraphs, linear strong R coloring numbers. You get a separator theorem. So the tree width is root n for n vertex subgraphs, and U itself has this low tree width coloring property. So these are many of the core properties of minor closed classes. And we have a single graph that contains the minor closed class, and it's got all the core properties. So why study a class of graphs when you can just study one graph? And this is the sort of the premise of this direction, is that, well, just study the single graph U and you get all the properties of the minor closed class for free. Okay, a really good problem is to prove this theorem without using the graph minor structure theorem of Robertson and Seymour. Is there a direct proof of this? I'd love to see such a proof. I think that would be very enlightening. Okay, just to wrap up, I'd like to talk about the most recent direction is on non-minor closed classes. And we have a generic way to extend these product structure theorems into non-minor closed classes. Let me start with an example. Here's a graph class that's studied a lot in the graph drawing community, is that say a graph is one planar if it can be drawn with at most one crossing on each edge. So here's a picture of a sort of an n by n by 2 grid. Think of it as three-dimensional, but I've projected it onto a flat plane, and now each edge has only got one crossing on it at most. So this is a one planar graph. Now this graph can contain arbitrarily large complete graph minors. If you think about it, if you contract the ith row at the front and then the ith column at the back into a single vertex, and you do that from I from 1 to n, you're going to get a complete graph minor. So these graphs can contain arbitrarily large complete graph minors, but they still have a nice structure. And this is the theorem we showed. It's a similar thing as for planar graphs. Every one planar graph is a subgraph of h times p, where the tree width of h is bounded at some number. It turns out to be 479. That's what it pops out from our proof. And you get this three-dimensional product as well, where the nice thing is that this tree width drops down all the way down to 3. So I think the punchline here is that these product structure theorems aren't restricted to minor closed classes. You can go beyond minor closed classes and get the same sort of product structure theorems. Why stop at one planar? Let's have k planar, where you allow k crossings on each edge. And you get a similar theorem. Every k planar graph is a subgraph of h times p, where the treewidth of h is bounded by a function of k, and we get this, in fact, it's big O of k to the 5. And then why stop at planar? We can put this graph on any surface with crossings as well, just because we can. Why not? Let's say a graph is g, k planar if it can be drawn on a surface of Euler genus G with at most k crossings on each edge. So here I've drawn a graph on the torus with one crossing per edge. But again, this is highly non-minor closed class, but we still get a product structure theorem for this class. Every GK planar graph is a subgraph of h times p, where the treewidth of h is bounded by the parameters. I think I'm going to skip this slide, which is a little bit about the proof. The point is that this thing called shortcut systems provides a generic method for moving from minor closed classes to non-minor closed classes. And let me summarize all these results here of tables of, on the left, you have the graph class. In the middle, you show what are all these graphs subgraphs of. H times P, where H has got bounded tree width, or in some cases, you have another little complete graph in here. In the middle here, we have minor, a graph class is excluding a minor. You get a tree decomposition over these sorts of graphs, bounded tree width times a path, complete joined with a complete graph. And down here, there are a number of non-minor closed classes that I haven't gone into. There's the same method that works for, say, one planar or k planar or GK planar, also works for something called map graphs. It works for powers of bounded degree graphs and several other things. Can all be described in terms of these products. So let me finish with some open problems. How far can we generalize these product structure theorems? The setting of Nessar-Trullo-Sohn de Mendes, the graph sparsity theory, provides a setting for answering this question. And they define something called polynomial expansion. And a good question is, can graphs with polynomial expansion be described in terms of products plus some other ingredients? And that's a massive question, basically asking what's the structure of graphs with polynomial expansion? And really, we don't know the answer, but I wonder if products are useful here. What if you take other products, h times a path times a path? What are the interesting subgraphs of these things? Instead of a path, what if you took a tree, or especially a bounded degree tree? And it's also good to think about application areas. There's a nice interplay between sort of theory building and problem solving here. And so if we go back to a problem application area like non-repetitive coloring, you can ask the question, well, do graph classes with single exponential expansion have bounded non-repetitive chromatic number? And to answer that question, what you then need to do is then build some theory and get a structural description of these classes and then answer it. So there's a very useful interplay between answering problems and then building theory to solve the problems. Finally, algorithmic applications. For those who are interested in algorithms, you think that this product structure theorem should be useful for getting efficient algorithms. There's a famous paper of Baker that produced approximation algorithms on planar graphs. And basically, Baker's idea is that if you take a layering of a planar graph, each layer has got bounded tree width. Well, this product structure theorem gives you a lot more structure than that. So you feel like it should be useful for getting algorithmic application. So there's a very broad question, but I think there's a lot of scope there for getting algorithmic results. All right, I'm going to stop there. Thank you very much for your attention.
Thank you very much, David, for a wonderful talk. Let us thank the speaker. Are there any questions?
So David, I actually have a quick question. So what do you know about those are there interesting graphs that you know that are subgraphs of H cross T for some tree T?
I really don't have an answer for that. We do know quite a bit about H times T. There's another paper that I haven't mentioned, and we sort of take a converse questions. We say, when is a strong product? When does it have either polynomial growth or polynomial expansion, or does bounded expansion? And we've answered that question completely for any product, H1 times H2, and then that includes things like H times a bounded degree tree. But I don't know any really good examples of naturally defined graph classes that are subgraphs of H times T. But H times T, as long as T has got bounded degree, has got several of the properties that H times a path does have. So it is a good graph class to think about, but I actually don't know of any natural theorems, naturally defined classes that are subgraphs of H times T.
Do we know that this is a strictly bigger class somehow? Just
yeah, it is. There are some properties that are different. Yeah.
Mm-hmm.
If you take T to be a complete binary tree, there's a big difference between a complete binary tree and a path. Is that the number of vertices at distance r from a vertex, a fixed vertex in a path, is only r, but in a complete binary tree it's 2 to the r, and that changes things substantially. So some properties that are related to expansion are very different when you go from H times a path to H times a complete binary tree.
And I guess kind of a related question of so if say we look at complete binary tree versus complete, tree of degree 3 or something, can we tell those apart as well? If it's H, if it's just to continue this question, if it's H times P, then it's different from H times a complete binary tree because of this growth condition. What if it's and then if you, instead of a complete binary tree, you look at a complete, like a T of a deregular tree or something.
Oh, I see.
Do the classes continue growing as you increase the degree?
They do continue to grow, but qualitatively the behavior doesn't change as long as the tree has got bounded degree. There's a big change from degree 2 to degree 3, but going from degree 3 to degree 4, there's not much change. So if you're just thinking about the properties in terms of bounded expansion, all you need is that the T has got bounded degree, at least 3 or more, but as long as it's bounded. But things change very much if you let T, say, be a star. That's an unbounded degree star, then that the properties change qualitatively at that point.
I see.
If you take an unbounded degree star times an unbounded degree star, then what you get is an unbounded complete bipartite graph, KNN, which is not at all sparse. So that's what happens if you multiply 2 graphs of unbounded degree. So you really want to, whenever you do a product, you want one of the graphs to have bounded degree.
I see. Are there any more questions?
Can I ask a question? So you mentioned this result about that planar graphs are minors of grids. So I mean, the grid doesn't have the diagonal edges; just has the horizontal and the vertical. So I mean, is there some hope that we can do something with a weaker product without the strong product, maybe like a different product?
There's some hope of getting something simpler, but whatever product you come up with, it has to allow infinite complete graph minors. Like we show that any graph that contains all the planar graphs must contain an infinite complete graph minor. So yes, there is some hope of getting something simpler, but it can't be as simple as a grid. It certainly can't be planar. I should say, if you go back to our with the theorem, and here, and this is the very first theorem. To answer your question, what you can actually say, if you take any one edge from H and any one edge from P, and then you look at this little 4, in the product, you have both crosses. But you can actually show that you only need one of the crosses. In this, every planar graph is a subgraph of this H times P with only one cross. But you don't know which cross it is. And for different edge at H and different edge of the path, you end up with a different cross inside the 4 cycle. So that answers your question partially. So that makes this H times P a little bit more planar, but it still is a non-planar graph, absolutely.
I see, thank you.
Okay.
Any other questions?
I had a question about the universal graph for minor closed classes.
Oh yeah.
You mentioned, I think the way it was phrased, you can exclude only one graph H. But is that H allowed to be infinite, or is it just with finite?
Is the excluded minor infinite? Is that what you're saying?
Yeah, is the excluded graph allowed to be infinite?
No, we prove it where X is finite. The excluded graph is finite. If you exclude an infinite minor, the behavior is different. There are several old papers on this, mainly by Robin Thomas. There's where on the what is the structure of graphs when you exclude a infinite complete graph, and the structure, the answer is different from when you exclude a finite case. And our theorem is just when you exclude a finite minor. Yeah, we haven't addressed that question in this product structure setting, and maybe there is something you can say there, but we haven't done it, and the answer will be different. Yeah.
Any other questions?
Yeah, I'm just remembering the papers to look at to answer that. There's a paper of Robin and Kriz, K-R-I-Z, and there's another paper, I think it's Robertson, Seymour, Thomas on that exact question.
Yeah, basically that's the same as you exclude the finite complete minor. So somehow says if you exclude the infinite graph as a complete graph minor, then you just get a tree decomposition where every total forfeits some finite graph minor. But the tree decomposition is more complicated.
Yeah, thanks, Chun Hung.
Any more questions? If I may ask, I actually have two questions. So one, since just we're looking at this slide, do you remember correctly that you said that later on that actually you can make this treewidth of H to be almost 7 instead of 8?
Yeah.
Do we know, could it be just 3 instead of?
Yeah, it could be 3. Yep.
Mm-hmm.
Yep. This theorem that's on the slide could be true with 3.
Mm-hmm.
But don't know.
Mm-hmm.
So we know it's not 2. There's a lower bound. There's a lower bound of 2. There's a lower bound of 3. Sorry, but yeah, we just don't know. I think I've pushed the current proof as far as I can go with 7. I don't think with the current proof you'll get below 7. It needs a completely new idea to go any further.
I see. And one more question in the theorem for minor closed. classes, you said that it is possible that maybe there could be a proof of this that does not go through the graph minor structure theorem. Could that then, assuming that, imagining that such a proof exists, can you then, could it be possible to then use this alternative structure theorem to prove, say, the well quasi-ordering?
I would be very surprised if that was possible, because these product structure theorems are weaker than the Robertson and Seymour graph minor structure theorem in the following sense. Robertson and Seymour's graph minor structure theorem can be paraphrased as follows. It says, for a given integer t, then the graphs that do not have kt as a minor can be constructed by a small number of ingredients. But then it also has this extra property that says that any graph that can be constructed by those ingredients does not have a kt prime minor for some t prime that only depends on t.
And
we don't have that. We don't have that property. That's our products contain arbitrarily large complete graphs as minors, so there's no such theorem. So I don't think we have any chance of really.
So in some sense, maybe it seems like maybe the minor close is not really the right notion of the graph class somehow.
Yeah.
For this.
So
this
really, these product structure theorems are sitting inside a bigger world. You're right, and that I think the right world is the graph sparsity theory of Nesetril and Osona de Mendes. That's where a product naturally sits. Yeah.
I see. Thank you. Are there any more questions? And if not, then let us thank David again.